some structure on the sets, and so the first structure, one of the most simple structure that we can give is basically a group. And we saw that a set with a binary operation, okay, so let's binary operation, and then we gave what is called, we gave a structure that we said this is a group, and then we started like looking up into the groups, what their properties are. We did not really look at any properties of group. We basically looked at some of the examples of groups. Now we'll get some, we'll try to see some properties of groups, and then again we'll come back to this mapping and this functions and mappings. But now it will be from a group to a group. So we already have given a structure to the group via the binary operation, and then we'll map one group to another. And this, if under this binary operation and in the second group there will be another binary operation, if structure is preserved, and we called it, we just said it last time, it was a homomorphism. Okay, so let's finally write down in a small part of the board the properties of a group. Let's say a set with a binary operation. Let's say star from G cross G to G will be called a group if it is associative. Second, if it is it has the identity element, existence of identity element. And third, we looked at that every element should have inverse element, should have an element corresponding to that, such that that element or other element multiplied to give you identity elements, called that inverse element. Okay, so these three properties, if a set satisfied under that binary operation, then we call it as a group. Okay. And we saw some examples, but some of the properties of a group is one, there, so property one is there exists only one identity element of a group or in a group. So you cannot actually have more than one identity element. There is exactly one, and not less than one, not greater than one, exactly one identity element that you have to take, that you have to give in this binary operation. Proof is very simple. Let us say E1 and E2 are two identity elements. Then what happens that E1 star E2 under, let's say, since E2 is an identity element, so it should be equal to E1 by the property of the identity element. On the other hand, since E1 is an identity element that we define, it should be equal to E2. So even if you give two identity elements, they have to be same, exactly same. So there is one identity element that you have to give. So the smallest set that you construct, okay, and give it a structure such that it is a group, you have to have an identity element. And the smallest set that forms a group is basically a singleton set. Okay, so you define a, let's say, set A, which has element A and nothing else. Okay, and you give the binary operation, let's say A star A is A, then it is a group. Okay, so this is the smallest group that you can form. Okay, just single identity element will be a group.
So while defining identity and inverse, we don't care about from which side the operation is being operated. It's like always abelian when we are talking about identity and inverse.
No, it's not we don't care about. We fix the properties in that way. That for the identity element, for not for other elements, for the identity elements from the left and from the right, it has to be same. That's how we define it. Okay, for the group. It's not that we don't care. It's just it's exactly defined in that way.
Okay.
Okay. For the inverse also, we actually have to have from the both sides
operation
is
is taken in the definitions.
in the definition. It's not we don't care about it. It's not also a consequence that if it is, let's say for example, for any binary operation, if you say G star, let's say G inverse is identity, does not always for any binary operation. For group, of course, it has to be the case. We have to define the binary operation in such a way that that has to be the case. But it does not always imply that G inverse star G should be. Okay, so it's not always the case. Okay, but we have to give the binary operation in such a way that this satisfies. I mean, not implies, but this is equal to this. It's a defining thing. Okay, so this is one, and second is given, let's say, an element G, there exists only one inverse corresponding to that. Okay. Again, let us say H1, H2 belongs to G are two inverses of G. Sorry, not capital G, small g. So by definition, we know H1 star G is equal to identity. Okay. And similarly, H2 star G is identity. Okay. This implies what we can do is H1 star G star H2 is H2 from multiplying with from this side, and okay, so this if we take the other way around, this also implies from the left if we multiply H1, okay, H1 star G star H2, okay. So here we are multiplying H2 from the right and we are multiplying H1 from the left. Then what happens that H1 times E is basically H1, and these two are same, you see. So we can say these two are same. So H1, even if we try to take two different inverses for a given element, they have to be same, exactly same. So these two are some general properties of this identity element and inverse element of a given element. Okay. And so these two are the cases. Okay. So now we come to the definition of subgroup. This is rather simple. Okay. So we already have given, let's say we already given a structure to the group, a structure to a set with all these properties satisfied. Okay. Now let H, which is a subset, so this is the notation of subset of G, okay, such that H itself satisfies 1, 2 and all these three under the same binary operation stuff. Okay, so G is a set and H, let's say H is a subset. Okay, and which by itself under the same binary operation satisfies all these three properties. Then H of course is a group, but this group is actually inside some other group under the same binary operation. So then H is called a subgroup. So this subgroup, sub-vector space, subfield and all these things will come over and over again. So basically whatever structure we have given to a set, and if some subset of that satisfies all these properties, okay, under the same binary operation, then we call it a subgroup. Okay, so given a group, if a subset satisfies all these things under the same binary operation, then it's a group. Of course, we don't have to explicitly check associativity because this is already there. Any subset you take, associativity will already be there because it's already given in this set. But so H must include identity element subset. Any subset of G will not work. Must include identity element, and every element we take in H, if we can include its inverse, then it's already a subgroup. So we have to check all these three properties under the same binary operation. So let's say simplest example of H could be, okay, given any group, simplest example of H would be, one of the example is very trivial. Just take the identity element of the group and you can say it's a subgroup. And of course, when we talk about in mathematics, of course, when we talk about subset, we actually, H may also be the same as G. It's not proper subset. It does not necessarily be the proper subset. So two trivial examples are, example one is the thing itself, the identity element only, and H, let's say, if we take the whole group, it's a subgroup of. It's a trivial statement, but generally mathematicians do in this way. They clearly define that when we talk about subset, we always have the option that the whole set is also a subset. And so this is abstract. For example, let us now take a slightly bigger example. Last time we introduced the symmetric group. Let us say today we will take symmetric group of 3 elements. Okay, S3. So how the symmetric group was defined? It was defined that if A has 3 elements in it, let's name them 1, 2, 3. Okay, does not matter much. Okay, so for S3, let's say A has 3 elements. Then we define S3 to be all the bijections from A to B. Right. So basically, its elements where the functions which actually gives the permutation between all these elements. Okay. So let us say the elements are, let us say phi 1, phi 2. So, and we saw that these elements are nothing. So the elements are basically the function which gives the permutation between these 3 elements. And how many numbers will be there in this set?
6.
Will be 3 factorial, which is 6 in this case. Let us say phi 1, phi 2, phi 3, phi 4, phi 5, phi trivially say that phi 1 is nothing but the identity element. That is, of course, identity element means which maps every element to itself. Okay, let's say phi. That means phi 1 is basically phi 1 of 1 would be 1, phi 1 of 2 would be 2, phi 1 of 3 would be 3. Remember, phi 1 is a map from A to A. Basically, what it will do, it will take elements from A and send it to some elements of A itself. And if we define in this way, then it's basically identity element. Because if we take further composition with this phi 1, we see that it does not do anything because it takes the same element to it. Okay. So let us, for the notational set, we define the elements to be not in this format, then we have to write more. But we will do, let's say 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. And we can write in this fashion. This is a very useful notation. This basically says that 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. So phi 1 we can write to be this. Okay. This notation means that what does phi 1 acts on this number and gives what? So that basically this arrow, if we remove this arrow, then it's a simpler notation. So what will be the elements of these things? So E clearly could be 1, 2, 3, 1, 2, 3. So in the top row, it does not matter how you write it. You can write 2 here, 1 here, and 2 here, 1 here. It does not matter because this basically says what is the map. But down row says that which maps to which. So that order matters given the ordering in the first row. Let us say phi 2, we have to give one more map. Let's say phi 2 is what? 1, let's say 1 goes to 2, okay? 2 goes to 1 and 3. So this is an element of, and let us say phi 3 is 1, 2, 3. Let's say 1 goes to 3, 2 goes to 2, 3 goes to 1. It's basically flip. This is flip of 1, 2. This is flip between 1 and 3. And phi 4 is nothing. So phi 4 let's define to be this map. Flip between 2 and 3. So all possible permutations. Okay. So in first we keep the identity. In the letter 3 we flip 2 of the elements, and let us say phi 5 is 1, 2, 3, and let us say now we cyclically permute this. 1 goes to 2, 2 goes to 3, 3 goes to 1, and phi 6 is 1 goes to 3, 2 goes to 1, 3 goes to 2, 1, 2, 3, 3, 2, 2, 2 to 1. So these are 6 distinct elements of S3. Now let us try to get the multiplication. By the way, apart from these 2 trivial examples, can you find some, let's say, subgroups of this group S3?
How inverse is defined? It's a phi 2 element. How what is the inverse of?
Find the inverse of phi 2.
2
Let us.
to 2 to 1.
Mhm.
It will take 2 to 1.
We don't I mean, if we give this structure and we say that S3 is a group
2 to 1.
under operation
Part of this.
binary operation. What is the binary operation here in S3? Permutation is here. A to A. Phi i's are the permutations of the elements of A. But S3 are what is S3?
Is a function of A to A mapping.
A to A mapping. So collection of all the phi i's. Right? Phi i's are the permutation functions, not S3. S3 is the collection of the permutation functions.
Achha, achha.
Right? And what is the structure? What is the binary operation we have given? So that means we have a binary operation we have defined in the last class, S3 cross S3 to S3. That means we take an element from S3, another element from S3, that means phi I, phi j. And what is this binary operation?
Composition.
Composition of functions. We took this binary operation to be the composition of functions. Because what are the elements of S3? They're functions. And natural that we saw last time, that what are the natural things we can do with functions? It's basically compositions. If it is from A to A itself, then we can compose as many times as we want. If it is from A to a different set, then it would have been a problem. But since it is from A to A, we can compose as many times as we want. Phi I, phi j, phi k, phi, and all these things. So this binary operation is basically the composition. So S3 is a group under which binary operation? It's the composition of functions. Okay. So now your question comes. Then why E? So particularly let's say, okay, let's define it to be phi 1. Why phi 1 is identified as the identity element?
Because if we compose the
Yes. For any phi j, composition of with phi 1 will always give us phi j. Why? Because whatever number we put here, out of 1, 2, 3, let's say A is 1, 2, 3. Okay. Whatever number we put here, let's say N, we put here, phi 1 will do what? So this is actually, the composition is always defined in this way, phi of 1n. Right? It's just the first thing acts on this element, then the second thing acts on this element. So we are spending a lot of time in this. Why? Because the linear representation that we'll be studying are basically some functions. Okay, it's basically linear transformation, linear functions. So that's why we need to understand this, like the composition thing, and what is the binary operation that we are giving. So that understanding is much more important. Okay, so now we already know that phi 1, what phi 1 does. Phi 1 takes any element and send it to itself. So this, the output of phi 1 m will always be m. So phi j m. So this means now if it happens for all the m's, then we can say that phi j compose phi 1 is phi j. It happens for all the m. So that's why phi 1 is an identity, and the other way around also. Okay, it's identity element. So that's why this is identity element. Now, if we want, let's say, what should be the, what is, so we did not explicitly say which is the inverse of what, right? Let us say the question you asked, that what is the inverse of phi 2? I can give you the answer. Phi 2 inverse is phi 2 itself. So the last condition, what it says, that under this binary operation, whatever binary operation we are providing, for every element we should have another element from the same set, such that under the binary operation they gives back me the identity element.
So
that means which phi j, let's say, what is the inverse of phi j? So let's say phi j is the inverse, and this should give me what is the identity element that we have already identified, phi 1. So which phi j will give me this condition for phi 2 as well as the other one. Phi j, phi 2. And my answer to that is essentially 2. That is simple in this particular case because 1 goes to 2, 2 goes to 1, and if we now do it again onto that, then 1 comes back to 1, 2 comes back to 2. This is understood? And this answer to this question will be a lot more easier, at least for the finite groups, if we can find the multiplication table. So let's find the multiplication table and see what happens. Okay, so let us try to construct the multiplication table in this case. This will be a big table, and let us see. Let us see. Let us say what is, so the binary operation, we take it to be the composition, right, between functions. So what is phi 1 compose phi 1? It will be phi 1 because we take phi 1, any element, we operate another phi 1, it will give me the same function, it's basically phi 1. And what is phi 1 compose phi 2, let's say? It will be phi 2 that we can explicitly check, and since this is phi 1 and it has already been established that this is identity element, so this part is trivial.
So for this group, all the elements are their own inverses now. For this group, all the elements are its own inverses.
What is phi 2 compose phi 1? This is phi 2. Okay. What is phi 2 compose phi 2? Phi 1. Up to this we have derived. What is phi 2 compose phi 3? What phi 1 does is 1, 2, 3, send it to 2, 1, 3, right? No, so phi 3. So this acts on the right. So we are defining in this way. Okay. So this is on the right, this is on the left. So we have to first take phi 3, right? Phi 3 first will act on the element, and then phi 1 acts. So what phi 3 does? Phi 3 takes 1 to 3, 2 to 2, and 3 to 1. What phi 2 does? 2 to 3. It takes 1 to 2. Takes 2 to 1. Takes 3 to 3 itself. Okay. Now we can remove the middle part and we check. And which is this? This is phi 6. What is phi 2 compose phi 4? Let's say. Again we can do the same way. So 1, 2, 3. 1 goes to 1, 2 goes to 3, 3 goes to 2. And then we add phi 2 on it. 1 goes to 2, 2 goes to 1, 3 goes to 2, 3, 1. 1, 2, 3. This part is same in all the cases. So 2, 3, 1. Which one is this? Phi 5. Then phi 2. So actually, in writing in this way, we have to erase a lot more stuff than this. So we'll do it this way first. This is trivial because this is identity. Okay. What is so? I'm going this way because it will take lesser time to compute. And then let's say phi 3, phi 3. So phi 3, phi 2. Sorry, phi 3, phi 2. This element. So first we'll write this one. This is the phi 2 will act first, and then phi 3 will act. Okay. So phi 3 acting of phi 3 is defined 1 goes to 3, 2 goes to 2, and 3 goes to 1. So this is precisely 2, 3, 1. 2, 3, 1 is phi 5. See, it's not commutative. Right? Phi 2, phi 3 is phi 6, whereas phi 3, phi 2 is phi 5. It's a different. Okay, so then phi 4. Let us now remove this part and act phi 4 on it. So this is 1, this is 2 goes to 3, 3 goes to 2 here. Right? So it's 3, 1, 2. It's phi 6. Phi 5 and phi 5, phi 2, right? Then act phi 5 on it. 1 goes to 2, 2 goes to 3, 3 goes to 1. 3 to 1. 5 3. Then 5 6, at 5 6 on it, 1 goes to 3, 2 goes to 1, 3 goes to 2. 1 3 2. 5 3. And one picture would be that these elements will appear exactly once. Here. 5 1 2 3 4 5 6 will not be repetitive. Okay. Now go to this case. Let us say we'll act phi 3 first. So phi 3 is already there, and then now act phi 3 on it. Okay. Again. So 1 2 3 2 2 2 3 2 1. 1 2 3 1 2 3. Yes, phi 1. Then let us say phi 4. So 1 2 1 2 2 3 3 2 2 3 1. This is phi 5. Right. Let us erase phi 1 because it's very trivial. Phi 1 is the identity, so it's not a big deal. And phi 5, now act phi 5 on it. 1 to 2, 2 to 3, 3 to 1, 3 2, phi 4. And then we can quickly guess which element will come here.
2.
Let us check that. Phi 6. Okay. So 1 2 3, 2 2 1, and 3 2 2. 2 1 3. Phi 2. Yes, it is indeed the case. Then we have to remove the phi 4 1 3 2. Let us write phi 4. What is this thing? Calculated. This is 1 2 3 होगा, 3 will go to 1, 2 will remain 3 1 2, and it is 5 6. And then let us do 5 4. So 5 4 1 2 2 3 3 2 2. This is 5 1. 5 4 5 inverse 5 4. And then 5 5 5 5. Where is this? 1 goes to 2, 3 goes to 1, and 2 goes to 3. 2 1 3. 2 1 3 is 5 2. And we can quickly check that it should be 1 2. It should be 5 3, right? Let us quickly check that. 1 goes to 3, 3 goes to 2, 2 goes to 1. Yes, indeed it is 5 3. Then this, let us say 5 5. 2 3 1. Interesting thing happens here. Okay. Let us see. First act 5 2. 5 2 is 1 goes to 2, 3 remains 3, 2 goes to 1, 1 3 2. 1 3 2 is 5 4, right? And then 5 3. 5 3 is 1 3 2 2 3 1. 2 1 3. 2 1 3 is 5 2. 5 4. 5 4. 5 4. Where? This one. 1 1 2 3 3 2. 3 2 1. 3 2 1 is 5 3. And then what else? 5 5. 5 5 is identity? No, it should not be.
5 6.
2 goes to 3, 3 goes to 1, 1 goes to 2, 3 1 2. It's 5 6. Now we have an exception. Earlier up to this 5 2 5 2 gives me 5 2 5 2 gives me 5 1, 5 3 5 3 gives me 5 1, 5 4 5 4 gives me 5 1. So they were their own inverses, but in this case it is not the case. Okay, and what indeed will be the case that 5 6 would be the inverse. Let's check that. 1 goes to 3, 2 goes to 1, 3 goes to 2. 1 2 3, 1 2 3. It's nothing but 5. Okay. And now the last column, without calculating, we can say what will be the element. I'm not calculating any further. So it will be 5 3. It will be 5 3 5 3. 5 1, 5 2 5 3 5 4, and this will be 5 1. So 5 2, and the rest two elements will be 5 1 and 5 5. 5 1. So this is our multiplication table. So from here we can check what will be the inverses. That's easy to check. And yes, so we check the element 5 1 because ultimately in the inverse case this has to give me the inverse element, identity element after multiplication. So let's say what will be the inverse of 5 4. It's nothing but take the 5 4 lines, go and check where 5 1 appears, take the number and you see that the inverse is 5 4. And what is the inverse of 5 5? That we saw that it's basically 5 6. And by the other property we can easily check that 5 5 will be the inverse of 5 6. So 5 6. Now you can easily check one thing, that in the subgroup what we saw that okay, the whole group is a subgroup. The identity element, take the identity element, make plus set, and that will be a subgroup. Other than that, let us take only this part. Okay? You see, this will form a subgroup. Right? Because if we take, let's say, only 5 1 5 2, and we see 5 phi 1 times phi 2 actually appears in this table. So this part is closed under the multiplication, has the inverses, identity element, etc. Similarly, if we take only phi 1 and phi 3, that will be another subset which will be a subgroup of the whole group. Phi 1, phi 4 will be another subgroup. But phi 1, phi 5 will not be a subgroup. Because phi 5 ka inverse, the inverse of phi 5 is not there in the phi 1, phi 5 set. Okay, so let phi 1, phi 2 is a subgroup, similarly phi 1, phi 3 is a subgroup and all these things, but phi 1, phi 5 is not a subgroup. But if we include the element phi 6, is it a subgroup? Is it? Let us now remove these things because these are not essential anymore. So what was it? So is it a subgroup? Why? So one thing has to be checked is that this is closed. So this under this operation. So let us take whatever possible binary operation we can construct. Phi 1, phi 1 is of course there in this. Phi 1, phi 5, phi 1, phi 6 will be there. Phi 5, phi 1, phi 5, phi 5 is there? Is it there in the group? In this set? What is phi 5, phi 5? Phi 6. So it's there. This closure has to be checked, right? Phi 5, phi 6 is identity fine. Right? Phi 6, phi 1 is of course phi 6, phi 6, phi 5 is identity. Phi 6, phi 6, phi 5. So it's there. So this is a subgroup, of course. Okay. So we got 4 different subgroups. Is there any other subgroup that we can construct? Of course, trivials are there. Phi 1 and the whole group. G itself is 3. So we check one element. If it is one element, then the identity element has to be there. 2 elements we have checked. There are exactly these 3, not more than 3. 3 elements. This is a subgroup. Is there any other 3 element subgroup in this group? Let us try, okay? Let us take phi 1, I have to give in any subgroup. Let us try, let's say phi 2 and try with phi 3. Okay. And try to check the closure properties. Phi 1 squared, phi 1, phi 2 is, of course, phi 2 is there in this subset. Phi 1, phi 3 is, of course, there in this subset. Fine, very good. Now take phi 2, phi 1. Is there. Phi 2, phi 2 is identity, is there. Phi 2, phi 3 is not there. So, in order to close the whole thing, we need to include phi 6. Once we include phi 6, we have to include phi 5. Right? And we can check that, again we have to check the closures. and it has to be phi 4, has to be included. So this is, so there is exactly 1 3 element subgroup. Is there any 4 element subgroup? Okay, with the same logic we can check phi 1, phi 3, phi 4 will not be there because these are similar calculations. Okay, and any other will not be there. Phi 5 के साथ will not be there. Okay. This phi 2, phi 3. Actually, there will not be any other subgroups of this. Okay, anyway, so that's not the point. There are other properties. Okay, so we'll not go into those details. So there are exactly 6 subgroups of S3. So those are explicitly phi 1, phi 2, phi 1, phi 2, phi 1, phi 3, phi 1, phi 4, phi 1, phi 5, phi 6, S3 itself. And I don't know whether we should introduce a concept of normal subgroup. Let's okay. Okay. So this is one thing. Now we come to the definition of homomorphism. The last time we introduced the definition, we tried to motivate the idea of homomorphism. Okay. Now we will clearly define it here. Okay. So let G be a group. Okay. Sorry, G and H be 2 groups, and a mapping rho, let's say if from G into H will be called a homomorphism if G1 star G2 is equal to f of G1 and f of G2. If this property is satisfied, then we'll call f is a homomorphism. That means, so this statement is understood. I have a group G, okay, let us say represented by this Venn diagram, a circle. So G is a group, okay, and H is another group. So there, let's say 2 different groups. It has a binary operation. Let's call this binary operation to be star, and this is H and its binary operation to be dot. Okay. Now, if is a mapping, so what it will do is it will take one element from G. So for any element we give, it will take some an element G to H, and that element is, let's say, if that element is H, is precisely given by this function of G, f of G. This is fine. So given any element from here, it will send an element to send this element via this rule, this mapping, to the other. And now this also has a structure. This also has a binary operation. For any 2 elements here, I can multiply. I have the binary operation. For any 2 elements here, I can multiply. So this rule says it will be called homomorphism if, let's say, I have G1 here and I have another element G2 here. So this all G1, G2. Okay. Take any 2 elements from this via this same group F. Okay, so G1 will let us say goes to H1 and G2 goes to H2. Right? Now, what this condition says, so G1, G2, before sending it to H, we can multiply here. Okay. So this multiplication will give me some other element, G3. On the other hand, H1, H3, H2 multiply together will give me some element, let us say H3. Let us say H3. Now, G3 via the rule will go to somewhere in this. Now the question is, whatever it will be F of G3. It may not be same as H3. But it will be called homomorphism if G3 is precisely H3. That means I multiply these two first and send that element to G, and I send the element first and then multiply them in the new group. If they are the same for any G1, G2, for any group, then it's it's a homomorphism. So what essentially says that whatever kind of structure the capital G has, the structure is kind of preserved in H also. So via this mapping, via these functions, what happens is that the structure, or if we say that this is the multiplication table, the same multiplication table will be there, similar multiplication table will be there in H also. So that's the kind of thing, homomorphism. So let us see some examples of homomorphism. Okay. So let us now take another note here. Okay, just write it down for checking. Let us take one example. Very simple example would be, let us say G is a group, okay, and B gives this mapping from G to G itself such that F of G is identity, or let us say H is another element. F of G is identity element of the group H. Let us denote it by the subscript H, capital H. Okay. So this is a homomorphism. How do we check it? The rule that I am specifying is it takes every element of G and set it to precisely the identity element.
What is the question?
No, the question is, this is an example of homomorphism. What is the example? G is a group, H is another group, and G, I define a function if from G to H, and the function definition is it takes any element of G and send it to identity element of the other group. The rule of assignment is this.
So any two element. Since G is a group, any two element G1 times G2 we leave another element
That's
in
simple
the
change.
group and
What we have to check? We have to check this condition. G1 times G2
EH times CH is also
is what?
EH.
EH.
Also, addition.
On the other hand, f of G1 times f of G2 is what? f of G1 is EH times EH. And in that group, this is identity element multiplication is EH. So these two are same. So what it says that you take all the elements of a group, send it to precisely the identity element, is actually a homomorphism. So by structure preserving, in this case, is slightly flawful. It's not exactly flawless. It's kind of structure can be shrinked. Okay, so that is allowed, but not that the structure is disrupted. It can be shrink to a single point or something like that, but not disrupted. It's kind of a structure preserving, but okay. So that's the definition. Okay, so this is example 1. Let us say example 2. Let us go to an infinite group. Okay. In the other day we had one example. Let us say example 2a. Let us say A is a set such that it is e to the power 2 pi theta. Theta is a real number. So A is basically the complex element of unimodular, whose modulus is 1. And B is a group which is cos theta, sin theta, minus sin theta, cos theta. So theta belongs to. So collection of all 2 cross 2, orthogonal matrices. And this is collection of all e to the power I 2 pi theta. 2 pi is it necessary? I don't think 2 pi is necessary. Yes, I theta correctly. 2 pi is not necessary. Okay. So now this we can check. Okay. Under simple multiplication, this forms a group. Let's take some element from A. So let us say theta 1, theta 2, 2 elements, e to the power I, e to the power I. And under this simple multiplication, this forms a group. It's a abelian group, but this associativity is there, identity element is, when theta is 0, it's identity, and inverse element of course is there. If we take, so what is the inverse of e to the power I theta? It's e to the power minus I theta. So this is the group. This is orthogonal matrices, and this will also form a group under matrix multiplication. So here binary operation is matrix multiplication, okay? Because matrix multiplication are associative. Identity element is of course there. If theta is 0, this is 1, 0, 0, 1, and inverse element is again theta being replaced by minus theta is your. Now let us give a rule from A to B such that f of e to the power I theta is sent to cos theta sin theta minus sin theta cos theta. So take one element. So if is a mapping, is a rule of assignment from A to B. You take one element from A, okay, which is characterized by this angle theta, and you send that element to precisely cos theta sin theta minus sin theta cos theta. Is it a homomorphism?
You could say that
Mhm.
if you do the matrix multiplication, then you will get the cos theta 1 plus theta 2 and sin theta 1 plus theta 2, then it will come.
Yes, and we know for the 2 cross 2 matrices this is cos theta 1 plus cos theta 2. Sorry, theta 1 plus theta, cos theta 1, cos of theta 1 plus theta 2, sin of theta 1 plus theta 2.
But if we're defining like.
Why am I giving?
No, no.
These are two groups. This is under
Oh.
ordinary complex multiplication. This is ordinary
Yeah.
matrix multiplication. This is very easy to check, right? No, but this is the rule I am specifying. This is the function definition. Just like we do in way for real numbers, if x is x square. This is the rule we set. That this is the rule I am setting. That take any element from A and which are the elements of A? Let's say e to the power some e to the power I theta, and it gives me the matrix. Fine. So this is an example with what is this? For this is a finite. Okay, there are infinite number of elements, so this is an example with infinite. Okay, so let us say 3. Let us say A is set 1 minus 1 precisely, and B is set 1 I minus 1 minus I. So under ordinary multiplication, we can check that A, B both are groups. Let us say if is a function from A to B such that f of 1 is 1, f of minus 1 is minus 1. Is this a binary homomorphism?
No,
This is not a homomorphism. Why not? Of course, this has to be a homomorphism because this is kind of identity map, right? 1 goes to 1, minus 1 goes to minus 1. Right? And it's basically, if we replace B by A, then it's identity map. I'm sending one element to itself, so it has to be a homomorphism. If sending same element to same element does not preserve the structure, then what will you do it? That's, okay, fine. So this is a homomorphism. Wait, let us define G to be a function from B to D. Okay. And for these four different elements, I'm specifying this rule. G is 1, G of minus 1 is also 1, G of I is minus 1, G of minus 1 is minus 1. Is this a homomorphism?
Yes.
Is it?
Yes.
Hmm?
Yes, yes.
Yes. Hmm? This is a homomorphism. So by these two examples, one, we can see that what is A? A has two elements, B has four elements. Okay. In this way, so two elements maximally can be mapped to two elements here. Okay, so this is precisely, let's say, by F functions, we are precisely confined to this region. So in a mapping, of course, we know that it does not have to cover the whole B, right? So this is F map. And for other map, what is this? This is G is in this direction, and B maps to the whole set A. But in this case, in the first case, in the F map, okay, so that is, we don't have a color chalk, right? So this is A. Let's forget about this for the moment. Okay. So by F map, we have one-to-one mapping. The structure is preserved as it is. Okay. But it does not, A does not cover the whole B group. Okay. But on the other hand, when we, let us take the G map, in this case, the structure is kind of preserved, but structure is getting shrinked. This multiplication table, whatever 4 cross 4 multiplication table was there, but that gets shrink to 2 cross 2. But still it is kind of structure preserving. Okay. So, these are the two things that I wanted to show by this example. Okay. Now we'll get some properties of homomorphism. Property 1 says if from G to H is a homomorphism, then f of E of, let's say, identity element of the group G has to be the identity element of the group H. That means the identity element will always be mapped to the identity element of the other group. You cannot do it other way around. You cannot send identity element and to a different element in the second group and call it a homomorphism. You cannot.
This is a definition or?
No, this is a property.
Oh,
We can derive it. Is that one. And B, f of G inverse is equal to, has to be f G and inverse of that. What does it tell you? What does it tell you? Let us erase this thing down. send the identity element to the identity element. Hello. Hi. So first condition tells that identity element has to be mapped to the identity element itself. Many other elements can be mapped to the identity element, that's not a problem. But identity element cannot be mapped to some other element in the second group. Okay. So this is easy to prove. So by the definition, what is this? If of E G star, let's say dot, if of E G. So EG can be decomposed into EG times EG, right? EG times EG. Now, but
No.
how can you prove it? I also forgot to do it. Oh, we should. Sorry. No, let's take any element from the group. For all the elements, now check these two. Fg is equal to Fg times.
So it has to write it.
So this has to take identity. Let's say for example Fg and Fg both are actual elements of H, right? These are after sending the G from capital G to capital H. So these are elements of capital H. So this is precisely the identity element. So one H set, and this is true for any G. That means any H has to satisfy this. One B, how do we prove it? The same way. Okay. So once this is proved, the other can be proven. So f of, let us say EH is nothing but f of EG, f of G times G inverse. This is fine. EH just from 1A, right? EH is nothing but E of f of EG. EG is nothing but G times G inverse for all G is equal to Fg dot f of G inverse. Right? So from this we can say that for all any G, this and this two are inverses. So this has to be inverse of Fg. This has to be inverse of Fg. So these two are the properties that are very handy in many cases. Okay. These two are the cases, and then I think this is fine. What else do we need to cover in homomorphism? The cardinal thing should be covered now or later. And third property 2 says that the range that we defined, f of g, is a subgroup of H. Okay, so this you can check. Okay. And definition, kernel. Kernel of G is defined as follows. Kernel of, let's say, G, kernel of F is equal to G belongs to G such that F of G is. So let us say kernel of
The second property is always true, no?
this one.
No, the
Yeah, this is true. This you can explicitly check that this has to be a subgroup.
no, I mean it doesn't have if doesn't have to be the homomorphism. For any something it will be true which takes G to H.
No, it has to be a homomorphism. It's not always. It has to be a homomorphism. No. What did you say exactly?
I said if a function takes elements from G and puts it to H, f of G is always a subgroup of H. If
Not really. Each might not have a binary operation defined in it. First of all. Second, you can send any.
it can be any set without a binary operation.
Yes, you can send.
Okay.
If is a rule from, see, when we define a function or mapping, we don't need to specify any structure in it. Right? We just send one element. So function is always thought of as one element sending to, it's being sent to one element in the second set. That's function, most general. When we give additional structure to the functions or we give some notation, then we say that this is the property. So the rule is assigned, and with that rule, this property has to be satisfied. Then we'll call it a homomorphism. Otherwise, it's just a mapping, normal mapping. It's just from set to set. G might have a structure, H might not have any structure at all.
But how can we prove that this is F has to be a homomorphism to hold this criteria?
Oh, this? No, this is not a necessary condition. This is sufficient.
Okay. Yeah,
If it is a homomorphism, then
it has to be a subgroup.
In general, it will not be.
In general, you take a subgroup, you take age, you take a subgroup and somehow send some rules, assign some rule, it will be a subgroup. That
It is
construct-
sufficient condition, not necessary.
This is not a necessary condition. This is sufficient condition. Anyway, kernel of F is defined to be the collection of all such elements of G such that the element goes to the identity element. That means, let's say in the notational sense, let's say G is a function. G is a group, capital G, and capital H is a group. Okay, and let us say there are group of elements. A subset which sends the elements to the identity elements E. Then this subset is defined to be the kernel of kernel of function F for a homomorphism, of course. Let us say F is a homomorphism from G to H. And kernel of F is defined to be the subset such that it sends those elements of the subset to the identity element of the second set. So for the first example, in which we send all the elements to be to the identity element, the kernel of the whole kernel of the function is basically the whole group itself. The example, the last example where we defined G one is identity, G minus one is identity, and Gi is minus one, G minus one is minus one. In this case, kernel is, this was, let's say, we defined in the last example 1 minus 1
1
is 1 minus 1 r minus 1, and we defined a function from b to a, which is a homomorphism. In this case, kernel is basically 1 minus 1. And property 3 says, property B, kernel is a subgroup. It is much more strong. There is much more stronger statement than this. This is a normal subgroup, but we did not introduce normal subgroup here, so that's why we are not calling it. But it is of course a subgroup. So kernel has to be a subgroup. Okay. So the image, the whole range is a subgroup, and the kernel itself is a subgroup. Okay, let us end this discussion now. We have covered almost many things we have covered in the group. So with this, we'll from the next class onwards we'll start vector space, and then maybe it will take 2 days, and then we'll go to the representation part. So these are being covered in some details, because these, so that whenever we need these properties, we can directly say that this is the property. We don't have to prove it again and again. So these concepts are well built, and we'll go to the representation part, and where these kind of things will be used and stated that this is trivial, so that we can do that. That's why this will be covered in detail. Okay.